This class is class 4, and we'll cover classification and regression. Now, we've seen both of these already, because really, classification and regression, that's sort of all a neural network does. So if I didn't teach you, just sort of throw you into classification and regression earlier, we couldn't really do anything. So now we're going to get into both of these deeper. I'm going to show you how you analyze the results from them. I'm going to show you several very standardized visualizations that you can produce using Matplotlib, which is built into the Jupyter Notebook, as well as, and you can generate these graphs and see them literally right there. I am going to show you only the most common visualizations. I think we deal with about 4 or 5 of them. I could completely bury you in visualizations because there are a ton of these, but I'm showing you the most common ones. I am also showing you some of the ones that they really like to, or at least from what I've heard from some people I've talked to and read, these are very common interview questions if you're going into data science or artificial intelligence or analyzing these. I'll show you which ones I like, which ones I'm not as fond of. Some of the ones that I'm not as fond of, a lot of people really like them, so you see them a lot in literature as you read through things. So before I talked about classification and regression primarily. There is another type of classification just called binary classification. It's a special case of classification. This is where you're classifying only between 2 different items. Some models only support binary classification if they're doing classification. A support vector machine, where you've probably seen it, where you have the dots and it draws the line between them. It's a very common neural or machine learning technique. Technically, support vector machines only support binary classification. They actually, at least the original algorithm doesn't even support regression. But somebody came out with, a little bit after the support vector machine, a version of it that does regression. So, but most packages that you deal with for support vector machines, they do in fact support more than just binary classification. What they do is, and we won't get into this because neural networks don't need it, but if you ever hear of one versus rest models, so one versus the rest, that's what they do. If your model can only distinguish between 2 things, so the iris data set where you have the 3 irises, out of the box, a support vector machine will not do that. What you have to do is do the one versus rest. So you would build 3 support vector machines, one that looks at iris setosa or not iris setosa, one that looks at iris virginica or not iris virginica. So you turn it into 3 questions. One versus the rest. Iris virginica or not iris virginica. And you build 3 of them for all of those. You get the prediction. Whichever model predicts the highest, that's what you classify it as. So you could do one versus rest on a neural network. You would just create 3 binary neural networks that have 2 output neurons where you're predicting between the 2. And you would do the one versus rest layer on the top. That's one of those things you want to do only in theory, so it's not one of the homework assignments because I've never actually done that, even just because. I find that it typically does not get any better results. I found it to get worse. From what I've read, it gets worse results for the neural network. So if your model out of the box supports multi-classification, you want to do that. Another reason that binary classification is very important is one of the most popular visualizations for classification called the ROC curve. That's all it works with. So the ROC curve is very popular. It's a little bit difficult to interpret if you're not used to it. So I cover it here because it's a very popular interview question. So and another area that binary classification is very popular is in the medical industry for tests. Typically, where you give somebody a medical test, either you have this disease or you don't have it. You're pregnant or you're not pregnant. These classifications. Really, what that test is doing is it's giving some number that determines, and if you're above a certain threshold, then you're considered to have the disease or not have the disease.
No gray area.
No gray area. Well, there is a gray area, and we'll see with the gray area how they really pick those. And the ROC curve gets into the gray area. That's why it's a very popular one to look at. So classification is more than 2. Regression is, in my day-to-day job, I deal a lot with regression. Usually we're regressing on a score. So we're regressing on, would we write insurance for somebody or would we not? And maybe their score is 10 if we would otherwise. So, and I deal with classification. Usually I deal with binary classification. So we are classifying on some behavior. Did they tell us they don't smoke, but they really do smoke? So I will classify smoker or non-smoker, that sort of thing, based on other information in their application other than the question, do you smoke? Which a certain percentage of people don't answer truthfully. It's a tricky question. Oh, I mean, like the vapor, what is that even classified as these days? And that's a gray area. Or I smoke a cigar, but only when I play golf, and I only play golf 4 times a year. So, yeah, and they do define that. And that's why they try to ask the question, have you used any tobacco product within the last 6 months? And then we'll ask another one, have you used any tobacco product within the last 5 years? And that includes smokeless tobacco. And it all depends. I work for a reinsurance company. So we're like the mortgage company that buys your mortgage after you get it from another company. So we have to deal with all the different ways that all these other companies ask this particular question and then normalize it into something reasonable. This is what we've dealt with before. So these are all the same encoding functions that we saw last time. So just look at the previous class notes because these are all covered there. There will definitely be a question or two about these on the midterm and asking you which ones you would use and why. Now, there's some new functions that I've given you that are kind of like these. These are just for feature vector encoding. You now have some visualization questions, or I'm sorry, ones. So there's 3 types of visualization that I'm giving you, at least at this point. The time series later, I mean, after we get past the midterm, which is in a few weeks, we will get into the really fun part of deep learning, which is what it's really, really built for. It can do this stuff, and it does this classification, regression sort of stuff that we're doing now really well, but time series and image recognition is where it really, really shines. So, and that by the way, is classification and regression as well. It's just different input data. And there's different visualizations you use for those. But for classic sort of predictive modeling, these are the 3 that you will see the most often, and they're very specific as far as when you use them. So that is defined here. So one of the most common ones that you'll see is the confusion matrix. That can be used for any type of classification neural network. That is particularly good for showing where say you had pictures of animals so you could use this for image recognition, and I've seen it used for that. But say your input data was types of animals. Maybe your neural network is really good at telling cats from dogs. So there's a special square on the confusion matrix that shows where your neural network confuses a cat for a dog. And maybe it doesn't do that very often. Maybe dogs and wolves are really hard because they look pretty similar, sort of. Depending on I mean, maybe not a chihuahua or something. That would just be crazy. But And if you're, so it tells you different things that the neural network gets confused about. Maybe classifying a truck from a car is easy, or is hard, but a truck from a motorcycle is pretty easy. So it shows you just the common pairs that your neural network gets confused on. And this is not just images. I may try to classify cigar smoker, tobacco smoker, whatever. Maybe given all the medical information, tobacco or cigar and cigarette smoker are pretty confusing, pretty similar. But cigar smoker and somebody who uses chewing tobacco, those are a lot more different. So the confusion matrix lets you see the types of classes that your neural network is getting confused on. The ROC curve is, okay, and by the way, confusion matrix, like I said, any type of classification network, don't use it on regression. It's useless on regression, and we'll see why. Confusion matrix can be a little confusing to read when you first read it, but it's not that bad once you understand it. Of all the three that I'm giving you here, I think the ROC curve is the hardest to read. So I will definitely take you through that and show you really what it's trying to communicate and the different ways that you do it. There is another metric that goes right along with the ROC curve called and we'll talk about that, called the AUC, which is the area under the curve. And don't worry, we're not going to get into integrals, but the integrals are commonly used to calculate that. You're just going to call a function, and how it calculates it, it actually draws a whole bunch of triangles underneath it and figures it out. It's the most common algorithm for that. So ROC curve is only used for binary classification. And then lift curve is used for regression, but never classification. So you kind of got this sort of patchwork of visualizations that you would want to use. And that is one of the questions that I give you on the midterm, where I show you basically some of these, and I just ask you to tell me kind of what that's really conveying to you. And you can Google even beyond the class, and you can Google how to read an ROC curve. There's tons of material on that. And by the way, what does ROC stand for? It's actually not important, but I'll tell you anyway. It's receiver operator characteristic. This is a curve that was originally, I think, created back in the 40s by electrical engineers to analyze radio waves. And it's almost, I'm sure the double E's still use it that way, but we basically just commandeered their nice chart and use it for something slightly different, and we still call it an ROC curve, but it's not like the receiver operator characteristic really means anything to what we're using it for. The lift curve, we'll see that one. It's just there's two lines and one lifts higher or lower than the other, and that tells you something. So all of these visualizations, you want to know, this is a common sort of, this is a common interview question. Just here's an ROC chart. What is this telling me? What does this mean? Here's a confusion matrix. What does this mean? And by the way, if you are looking to go in the data science profession, there's a really good site that has a link of, just do top interview questions for data scientists. And also sometime in October, I don't even remember the date offhand, but I am giving a presentation here at Washington University on common questions, and not just from data science, because I actually have a lot more experience interviewing and technical interviewing IT professionals than I do data scientists, but it's, I think it's October 19th. I don't remember. Does anybody remember? There's been an announcement sent out, but I will send information out on that when it gets closer. But it's on a Wednesday. Okay. So these are the functions that actually produce these. I am really not in this class trying to teach you how to use Matplotlib. Matplotlib is awesome, and I am far from an expert in it. They've got really good, they have extremely good documentation, even by open source standards. They have just almost a gallery of, if you want to do anything in, and this is also kind of sad, the guy who created it died a somewhat premature death, but the community has very much taken up the mantle, so to speak, and continued it on. This is very much based on MATLAB, so if you're used to that, it'll be very similar, but you can do all sorts of really cool visualizations, and they have all kinds of examples of what these look like, and then the Python code right next to it to show you how to do it. So if visualization is something you need to do, which usually you do, that would be, I've seen entire classes taught just on visualization using Python and Matplotlib. The school that I'm in the process of hopefully getting a PhD from had one class like that. I did not take it, but it was. So the individual commands that you have here, I am really, like I said, I could do a whole class on this. These are functions, I created each of these. So if you plot the confusion matrix, we'll see examples of all of those, but basically scikit-learn has a function that generates the confusion matrix for you. Usually I actually like looking at the confusion matrix in matrix form, so just literally the mathematical matrix with the brackets, rather than graphical form. So you can print that out and see it. And then the names are just the names of like the iris, the three irises, just a list, and we'll see that. And then it basically plots it. Yes, let me see what happens. So it'll give these, which are fine. Those are actually not, those are warnings that only show up the first time you run it, and if you run it again, they actually don't show up, which I don't know what's going on behind the scenes there, but the warnings are fine. And then plot an ROC. I tried to make these as consistent as possible so they're really easy to call. Basically, you pass in your predictions and then you pass in the real values. And you do the same thing for the chart regression. And we saw the chart regression function before in last class. I just didn't explain it very well, but showed you basically what it was and try to get the two lines together. So those are all the functions. They're not really that complicated. There's not a whole lot going on there. Largely what you're doing in Matplotlib is you're creating the legend, so you're setting the Y labels, and then you actually show the legend. These plot commands, so basically the lift curve has two lines, so that's why I have two plots. You're basically just passing it a list of the Y's, a list of the X's. It is very important, though, that you do this sort. And we'll see why that sort is necessary when I show you how to read it. Okay, so binary classification. This is inherently, binary classification is not that complicated. You're just dealing between two things. But when you deal with binary classification, particularly if you're dealing with anything medical or a test, do you have the disease, do you not have a disease, you very quickly get into the area of just statistics 101, where you have the sensitivity and specificity, type 1, type 2 error, that sort of thing. And these can be important when you communicate with people who work more in a medical background. For me, I work with them quite a bit because we have our underwriters who are very A lot of our more advanced senior sort of underwriter leaders have come from backgrounds where they're RNs. We have, I think, about 4 or 5 MDs on staff that help us with that. So we get a lot of this sort of terminology. So it's important to think of that. If you're dealing with a medical test, you're going to have, whoops, didn't want to do that. You have, basically, if you're dealing with a medical test, it's positive or negative. Those are the two things you're classifying between. And I give you a new data set to deal with because the iris data set would not be particularly good for binary classification. I've seen examples where they do it, where they basically have you classify between it is iris setosa or it's not. And basically you can turn it. But the iris data set is really, really easy as a 3 class classification. It's trivial, simple as that. So this is just to show you what this data set looks like. This is another UCI data set. And this is a page on my GitHub site where I just give you some basic information about it. It has an ID column. Usually when you have ID columns, they are completely unimportant and you can strip them. When you're dealing in the real world, usually they're very important and you need to keep them around so that when you do generate predictions, you can say, here's my prediction on ID number 1000, so that whoever requested the predictions from your model can go back and see where they're actually at. But you don't want to send the IDs into your model because they will do nothing for your predictiveness. And if they do, sometimes they will, because you might find that all the IDs, maybe you're trying to, a really simple example is, say you're trying to predict if a policy was issued under one agent or another agent. You probably wouldn't want to do that, but maybe all of agent A's happens at the beginning, all of agent B's happens at the end, and those ID columns are extremely predictive. But you would never have them again because when you go to write new business, they're just going to be at the end. So you always want to remove ID columns. If they are giving you predictiveness, it's usually bad, because that's information you won't have when you're running the model for real. Diagnosis, this is your target, so this is what you're trying to predict. It's a binary classification, so benign means that they don't have cancer. It's a tumor, but it's not a cancerous tumor. And malignant means that it is cancer. Now, we're not trying to diagnose if the person has a tumor or not. This is a case where they have found an actual tumor and they are trying to determine if it's cancerous or not, if it's malignant. So malignant, that is going to be 1, that is going to be positive. Benign is going to be 0, negative. And these are all these other values that they have. And this is actually a really good example of feature engineering. Because if you look at this, they talk about the mean radius. So basically a pathologist was sitting there looking at a microscope, and when you look at a pathology report, what you're looking for to determine if something is cancer or not is how quickly are the cells dividing. If they're dividing extremely quickly relative to the other cells, that's usually a bad sign. And that's how chemotherapy works. It attacks the rapidly dividing cells, like your hair cells, which I don't have many of to begin with. But that's why they all die off. So what they're doing is, probably a pathologist wrote down in the report the radius and the texture and the parameter, the length around, of certain cells. But when the doctors, so if you read the original paper that this came from, they tried to summarize this with feature engineering. They don't want to send all that data at the neural network because, say, maybe the first pathologist read in 10 cells and the second one read in 20. You need to have that fixed feature vector. So they summarize it. What's the average? What's the mean radius, the mean texture, the mean parameter? This is very, very common, and the original data that they calculated all of these means and averages from, you don't have access to. They did not release it with the paper. But this is very common. You will see, I mean, in our underwriting data, maybe we're looking at traffic tickets that somebody's got. What's the worst one that they got of the batch? What's the worst severity? And we'll put that into a particular field. It gets more complicated than that, and you keep rerunning it until you get a good prediction. And this is what the data looks like. See all the IDs. You basically want to strip those. The diagnosis, benign and malignant, and then all these various radiuses and other things. And the ... there's just too many of them. That is a very good question. You would only know that by looking at the original paper, but it is the mean for this row. So each row is a patient, and it is the mean for that one. They don't do, I don't think they do a standard deviation, so, and that is very often a comparison that you might do. If I wanted to engineer this further and try to create additional features for this, what I might do is calculate for two groups, so the benign group and the malignant group, I might calculate two means, one mean for the malignant, one mean for the benign, and then calculate the number of standard deviations different this particular patient is for your average benign, your average mean. That might, or your average malignant. That might carry some information for the neural network to help it do that. That's a very common feature engineering technique. Because feature engineering is all about doing the math, saving the neural network from having to do a lot of mathematics. And to do that, I would have to break this up into benign and malignant, calculate two means, calculate a standard deviation for each of those, and then create two new columns. How many standard deviations are you from the benign group? How many standard deviations are you from the malignant group? The neural network's not going to do that. It might approximate something kind of like it, but that might be a useful engineered feature. I'm not at all suggesting you do that when you calculate this one. So if you look at it, this is also a really good example of building a feature vector. The ID I drop, and then I use my functions, and I use a lot of them. So I encode them as numerics. I'm sorry, I encode that one as a z-score. For this one, was encoding them as indices because there's not a whole lot of them, so I was encoding them as a classification. I would be just as inclined for this one to use a z-score, and to be honest, this is something that I was experimenting with, and I thought I had left my z-score version there, and this gets actually surprisingly well, surprisingly good results. And this, oh, I remember what I was doing. Yeah, I did this on purpose. So I'm going to put a comment in there so that we have that. So I'm sort of intentionally making it not get as good of a score. The z-scores do better than the text indices. Usually you would only do the text indice like we saw last class on a categorical, like the state that you're in, something that is a text field. And then, just like we did last time, I convert it into the X and Y. Diagnosis is the target. I do split into a train test set. 25% for train. I'm sorry, for test, for the validation. I create a TensorFlow, a fairly simple one, Again, I'm not necessarily doing a really complicated neural network because I don't want this to classify it too well, because then the ROC curve is quite boring. And I'll show you what a perfect ROC curve looks like. I do define the early stopping, so if it's consistent for 200 rounds, it will stop. I fit it, and I report a final accuracy. So usually you want to use accuracy if you're dealing with classification, just like before. It's another metric. It's not a fancy visualization metric, but ignore the warning there. That is just telling you something that they're going to change in the future. And here, basically, I train it through the epochs. You can see the training score going down, the validation loss going down. It eventually settles on an 84% accuracy, which is, for this particular data set, is pretty good. It can actually go into the 90s if you tune it more. I've seen that happen. This, by the way, is one of these data sets that is on UCI, so it has been beat to death by researchers. There's lots of literature for that. So the confusion matrix. You can use a confusion matrix on any type of classification network. You can use one on a binary classification. It's pretty simple looking. So what I'm doing here is I'm calling classifier.predict. The thing to note there is I am doing predict and not predict proba. I showed you predict proba last time. All it's doing here is saying, does it think it's malignant or does it think it's not? It'll give you a 0 if it thinks it's malignant. I'm sorry, it'll give you a 0 if it thinks it's benign, a 1 if it thinks it's malignant. You don't care about the probability. So this is the yes/no. You have it, you don't. You're pregnant, you're not. All these tests, they're all calibrated in such a way so that at the end of the day, it gives you a yes or a no. But really, underneath almost all of these tests, there is a underlying sort of probability at work. Like the diabetes test, the A1C blood test. There's a number that you're always given there. At the end of the day, your doctor will tell you, well, you're borderline diabetic, you are diabetic, or you're normal. But there's a number there that's what's coming back. Here, we don't care about the number. We're just saying, is it one or is it the other? And there's this very handy function that scikit-learn gives you that will calculate a confusion matrix for you. And you just call that. You give it the expected outputs. So y-test are your expected test outputs, and pred is your predictions that you generated above. And it generates a confusion matrix, which is truly a mathematical matrix. And then this is just a command that I'm doing that causes me to only get 2 decimal places. I'll put a comment in there for that. Otherwise, your matrix looks really obnoxious. I'm going to save and checkpoint so I don't lose this. And then, so there's 2 confusion matrices that you will see. There is the raw one, which is the first one, and then there's a normalized one. The normalized one is more like an accuracy score. So you're getting almost an accuracy score between every 2 things. Whereas the unnormalized one, the raw one, is a count. So when we print out the confusion matrix, so that's what a confusion matrix actually looks like visually. We'll look at the visual one first. So sometimes different versions of the confusion matrix will flip the x and y axes, but usually the y-axis is your true label. So either it was malignant or benign. This is what the person was determined beyond any. And when you get into this really, really at the advanced level, true. True according to what? How do they know that the person truly had breast cancer? Did they die of it? Whatever. So, but here we're just assuming it's truth. It's what the pathologist actually determined. We're trying to teach the neural network to do the job of the pathologist. So the pathologist said it is truly benign or it is truly malignant. This is what the neural network predicted. So this is why the diagonal, that's the first thing you always want to look for in a confusion matrix, is the diagonal. So when you're trying to read these, you want to go for the diagonal. Notice the normalized one looks pretty similar too. The diagonal, a good confusion matrix always has a dark diagonal, because the diagonal is the cases where the neural network or the model, because you can use these on any model you really want to, was correct. So ideally, these two would have been the same color, but this neural network did make some errors here. So that's why you have the lighter blue. If you have pure snow white, that is the same white as the back of the screen, that's good. That means the neural network never made this particular error. So when you've got a binary classification network, there's really only two errors you can make. Either they were benign and you classified them as malignant, which is what it did in a few cases, or they were malignant and you classified them as benign. Classified it really was benign, and you classified it as malignant. That's the false positive, my mistake. You predicted malignant, it's not, that's a false positive. You predicted benign, but it was. They really did have cancer. That is that's the false negative. You gave them a negative, but it was really positive. And the reason, this is what accuracy does not tell you. If you just use the accuracy number, it just tells you the percentages where it was wrong. Usually you have to decide which is worse, and often one is considerably worse. Mm-hmm. So if you make the mistake and you say that somebody had cancer when they didn't, what's going to happen? So you have to decide what the possibility is. So on one hand, they get a lot of treatments that they didn't need, but what's the other possibility? They had cancer, but you tell them that they did not. Most likely, they would become even more symptomatic, and they would come back for further testing, and you would figure it out. But now you've lost critical time. So it's a value judgment, and that's why the doctors will very often say, well, you were actually very borderline. So they usually won't give you just the pure positive, negative as they're looking at things. I prefer to look at them in this form. So again, you can see the pronounced diagonal. You can see that 67 cases were here, 51 cases were here, 22 were incorrectly classified there, and only, I'm sorry, I'm talking about the normalized one. So these are percentages. 75% were here, 94% were here. Now notice how they have to add up. They have to add up across the rows.
So then ideally you want their two diagonals to be like...
Yeah, I mean, perfect would be zeros here and 1.0s all the way down the diagonal. That would be a mixed blessing. That would be a really good score, but it would also be a model that I would not trust, because I would be afraid that something went wrong, that I had given it some piece of information that it would never have in the real world, or that the data were too small and it just overfit it, it just memorized if I wasn't using a validation set. So that is how you look at it. Sometimes I care about the numbers. This is why I like the numbers better than the colors. If I were to just make a guess, I would guess that was a perfect square, that was 0, that was pure white. But you can see that there are really, you can see that, so I really like to look at all of these. I can see, okay, that's really only 6%. But then 6%, what number is that really? Well, that's only 3 cases. Another thing that is very important to do on these is if you look at if you sum these up, here they should add up to 100, but if you sum them on the non-normalized ones, that will show you that, okay, there is 89 up here and only 54 here. So it's not even. You don't have the same number of malignants and benigns. You have actually, if we go down to the thing, you actually have more benigns than you do malignants. All right, we will go ahead and continue. I am going to pass around the sign-up sheet, and I do apologize. It's a little bit wrinkled. From those of you who were in here when I was setting up, I accidentally knocked this over with the cap on, so if you're wondering, what in the heck did he do to this thing? I just knocked a little bit of smart water on there that I very dumbly knocked over. So and like I said, I think most of you were here, but I'm just keeping track of where people are. If you can't make it to class, just send me an email and I will manually mark you, but just so that I have an idea. I know we do have it so that you can listen to the pre-recorded materials. So just write your initial by your name and pass it around, make sure it gets to everybody. And if you've already moved to the paperless society and don't have a pen, borrow one from your next door neighbor. And then whoever it gets to last, just if you could just drop it up on my desk. Okay, so, and then the text is largely just what I described already. So ROC curves. ROC curves, you see them a lot in data science. So I do want to explain them. At my company, I have in the, I guess, 5 years that I've been in the analytics and data science group, I have never once used them. I have seen somebody use them, and after spending the first half hour of the meeting explaining just how to read them, he never used them again. So an ROC curve, there are a lot of sites that have very good descriptions of how to read them. They are dealing with false positives, false negatives, and true positives, true negatives. They are very much dealing with a lot of these tests. It's all how you set the threshold. So if you're training a neural network to predict if that cancer cell or if that tumor is malignant or not malignant, you are going to get some probability out of it. You're going to call predict proba, and you're going to get that probability. And this is important, so let me make sure that you've seen, because you saw predict proba last time, but if let me actually run it. That also makes sure that all the code compiles, which it did, as of last night anyway. I'm going to run that. And that doesn't produce an output, which is fine. Then I'm going to run this. And you'll see, hopefully, the neural network start to train. So it's training. Then we run the we run this, and we get it regenerated the confusion matrix. So what I could do is I could call this down here. Oops, not down there. I could call this here, and instead of doing that, I'm going to do print. And I'm going to do predict proba. And there's examples of this in the last class. But if I call it now, it's going to generate these, and then it prints out a whole bunch of these. And those I really dislike that it uses the scientific notation for this. But scientific notation, what you're basically seeing here is that means shift the decimal place 1 point here. So this is 0.75. So that's telling you basically that you have a 0.75% probability of being benign in this first case. I'm sorry, of having it because it's 0, 1. And a 0.24% of benign malignant, so that would be 2.4% of being benign. The question that you need to ask yourself, though, is what's the cutoff? So this is a 75% probability of cancer. What would you tell that patient? Would you tell them they have cancer or not? When you call just predict, it would tell them that that they did, because it's going to pick whichever of these two numbers is the highest. That's what predict does. So as you go through these, you can see the various levels. So you need to figure out where you're going to put that threshold. Now I'm going to remove that command because it makes my my output very ugly. So what you very quickly get into, and these are, I've seen the actuaries actually ask this in interviews where they just want to make sure, do you know sensitivity versus specificity? Do you know true versus, do you know type 1, type 2 error? This is all the same stuff you learn in Statistics 101. So a type 1 error deals with how bad are you on false positives, true versus false positives. A type 1 error, that's a sensitive test is the type 1 error. A specific test is a type 2 error. And the specific is dealing with how good is it at classifying if you're negative, if you don't. So a very specific test deals real well if you're dealing with false negatives, or is real good at telling if you don't have the disease, less accurate on telling you if you do have the disease. The type 1 error, a sensitive test, is basically it's better at telling if you do have the disease. And then so this is all about how do you specify that range. So if the neural network told you you had 0% probability, usually you'd want to treat that as a negative. So this is the true negative range. If it told you you had 1.0, so it's dead certain, That would be the positive. So that's more sensitive, more specific. This is your cutoff. So basically your cutoff, you can put this wherever you want to. And that's how you tune the network for if you want to be more specific, if you care more about false negatives or false positives. That range. This is the important part. This is how you read a rock chart. And this is the part that I deal with primarily when I do have to read them. And usually when I'm reading them, they're in scientific literature that is using them. So what you have to look at is basically this is looking at if you're willing to accept a 0% true positive rate, what is your false positive rate going to look at? So it's looking at the interaction between those two. So usually, always the line will start in the corners. Because if you're willing to accept a false positive rate of 0%, then the other is going to be quite good. So no predictivity, where basically you're flipping a coin, so from 0% to 100, that is no predictive power whatsoever on the for the model. If you imagine taking this line and pulling it all the way to the upper corner, that would be a perfect model. That would be a model that always predicted the number of true positives it had would be it would never have a false positive, it would never have a false negative. Most models will land somewhere in the middle here. A near perfect would be somewhat up there. A real one, like we see when we plot it here, looks something like this. So you're always going to start in the corner, you're always going to end in the corner. This one, what this ROC chart would tell you is it is better at reading, it is better at dealing with the, it doesn't generate as many false positives, or it generates actually more false positives than it does true positives, because it's more within that range. So you look at, if you drew an imaginary line to there, what part of it, what is the area there? Is the area out here is the error. The area down here is correct. So if you draw the line there, you can see that it's generating more false positives than it is true positives. So as you set it higher, in both corners, it's going to be, so the true positive rate versus the false positive rate, here you don't have any false positives. And you have all true positives, but you're missing all of the false negatives. So if you set it at either extreme, you're either going to catch all the positive cases at the expense of all the negative cases, or you're going to catch all the negative cases at the expense of all the positive cases. And then the other metric, I don't tend to analyze that all that much, looking at the difference. If I did more sort of medical tests, I would probably deal with that a lot more. What I'm usually interested in is the area under the curve. So the area under the curve, which it calculates for you, you don't have to, and usually you don't take integrals, derivatives, there's two ways to take each of them. You do a symbolic derivative where you move the numbers around. I'm sorry, the equation around, and you take literally the derivative of it, that for integrals, it's sort of the same way. You either symbolically solve the integral so that you have the integral. You don't do that on this because you don't know what the formula is. So you can't just take the integral of this. You've got to do one of the numeric integral values where you estimate it. The usual approach that in math, often they show you just put a bunch of rectangles under these and calculate the area of the rectangles summed together. There's a very common ROC, AUC, what you call that. They do something a little more accurate than the rectangles. They use a bunch of triangles underneath it. And I have never once worked through that algorithm. I know how it works in general, but have never actually gone through it. Integrals, I'm usually and this is very much a percent. So the area of the entire thing, since we're dealing one by one, would be 1.0. So, like I said, you will see these in general. What I would say to know about them is just the closer this is to here, the better. If it's a straight line, it's a nearly worthless model. If it goes below the line, it's actually, on something that's a 50-50 case, it's not even getting 50-50 correct. So what that usually means is you just have a really, really small number of either positives or negatives, and it's not even getting that right. Where you can achieve this line by basically, if you realize that it's 50-50, you have 50% are malignant, 50% are benign, then just flip a coin. But if you realize this is a really, really rare test where maybe you are, let's do something outside of medical. Maybe this is a IQ test, and positive means that you're, I don't know, 150 IQ, something just off the charts crazy high. That's positive. Negative is everybody else. You want to do 50-50 on that. Even if you were just going to write the most basic model. If you said 50-50, you would score something very below the line. To get the line, to just make a rough guess, you would say not a genius or not 150 IQ, because most that you're going to run into are not. So if you're dealing with imbalanced data, that is usually the criteria that they want to measure you against. So if I'm looking at, is somebody a smoker or not a smoker? The dumb benchmark model that I would want to compare this against would be not a smoker, because most people in the United States, I think 14%, are smokers. So if I wrote a model that just always said smoker, yeah, it would fall below the line. This has to be 2. There are variants of the ROC chart that you will see where they have more than 2 classes. You're just simply going to have more than one blue line. I'm not going to force the model to be worse than it was. I always want the best possible model, but when I'm seeing a model in the upper 90%, I don't trust it. I am really worried about, okay, what did I screw up? I probably did something wrong. I probably gave it data. Because when I get data to build these models for in an actual corporate situation, I get maybe like 30 tables, have to join them together and get the feature vector, and then I worry about, is there something that came in, like if we're trying to predict, was a claim fraudulent or not? And I have a column that tells me if it is, and that's the target. But maybe there's another column hidden in there that gives me a really good indicator that it was fraudulent, like was investigated. Because you have to think about this. In life insurance, claims only happen after somebody dies. We're not going to investigate the claim prior to it happening. And you didn't do a good enough job of filtering out all the too good to be true data. So if I see a model shooting up into the 90% range, 95, then I'm worried about it. hidden neuron counts sometimes, but largely, usually I start high with hidden neurons and start bringing them back to get a more simple neural network until I see that performance is starting to fall. What I look at is feature encoding. So how can I re-represent the data in a way that the neural network can learn from it better? And one of the chief things that I will start to look at is looking at some of the distributions, looking for the bimodal distributions where you have sort of the hump where there's two modes, and I see that, okay, this one, there's clearly two groups there. And if I can engineer another feature that tells me which of those two groups that person is in, that might be very helpful to the neural network. So where we typically spend a lot of our time is just data representation. You get the data, it's in all these columns, but then you start to see which, and this is something we look at next time, which is very, very useful. We look at feature importance. So you've got all these inputs coming into the neural network, like we have in the breast cancer one. All these inputs, lots of them. How many of those are really important? Which one of them is the most important? We'll see next time how we can actually determine that. And I will start to look at the most important ones. I forget which of these are the most important ones. It's been a while since I looked at this data, but maybe mean area is really important. And the worst area. Maybe the difference between those two, the difference between the average area and the worst area, maybe adding that field into there might give the neural network some additional predictive power. So once you've sort of created the first neural network, you've trained it as best you can, you've tried various levels of hidden neurons, and that usually doesn't give you that much of a gain unless you've just starved it of hidden neurons. It's going to give you something approximate of what it's going to do. Then I start representing the data in different ways. Steps I would not worry about because I will almost always be using an early stop. So steps, I often set that at 1,000,000. I don't care. Just go for it. Learning rate is very important. We'll see more about learning rate next time. If you're using one of the more modern algorithms like Adam, it's a lot less sensitive to learning rate. But learning rate, what I will often do is set it to something reasonable like 0.1, see what that does. Then I'll try 0.01, move it down, see if that's giving me a better approximation. You used to have to deal with another parameter called momentum. Most of the modern training algorithms will simply define that for you. So the most important ones are learning rate, and then just the number, just making sure you have the correct number of hidden neurons. And then often I will set the learning rate very, very low, realizing that that network may train overnight, but it might give me a very accurate representation. And then neural networks often too, you ensemble them together because neural networks are starting with random weights. You might train 10 neural networks and average them together. We see that in the second to the last class. I show you how to, that's very important. And then you might also ensemble the neural network with a second type of a model called a gradient boosted machine or something. GBM, gradient boosted machine, is currently one of the most powerful machine learning algorithms there is. And it ensembles really well with deep learning. Decrease or increase, or you might deal with for us, we might deal with an entirely different geographic region, and the tests are different. Basically, we're putting different data into it, and the prevalence of certain diseases are very different in different countries. So the model might not perform as well, and then we need to calibrate it or create a whole new one. It's just if I know if I go to my boss and tell him I am predicting people who lie on smoker status with 98% accuracy, he will tell me, okay, make very, very, very sure you're right and that your model's right. And we have all sorts of ways that we go through to verify them. It's just the more accurate the model is, the more skeptical we will be. We won't not use it. I mean, we sometimes have very accurate models in certain areas, but it's a very, very important part of our job is making sure that the models are actually, that's an ongoing benchmarking process that we definitely do. And new data coming in, we trust that tremendously because we know it's not been mined out of the database and it might have had some other data coming with it that we shouldn't be using. If it's doing really good, I mean, if you've trained a model on the stock market and you run it and it on new data coming in and it's predicting quite well, you trust it because it's performing well on current data. What threw some of the stock market models, though, was when fundamental economics changed, like 2008 and other things. So that caused some of them to have to be refit. Okay, so back down to here. So like one Kaggle competition, predicting a biological response. So this was very much a binary classification. And I'm going on my memory here, but in Kaggle competitions, the evaluation link always tells you how you're going to be evaluated. Now this one actually uses something other than area under a curve, but this is one where they could have done that. So a lot of the competitions, they will want you to maximize the area under your curve. All right, regression. This is the last one that I'm going to show you. This is a lift chart. We use these all the time. And it's a regression only. This one can be a little strange to interpret. One of the first things that I always want to know when I'm looking at a chart is, what do the axes mean? So it's very important to remember what the axes mean in the lift chart. The output, the y-axis is always the output. So you have basically, this is the miles per gallon. So the output is from 10, so I guess there were not any cars that had worse than 10 miles per gallon in that data set, or close to, up to 50. So regression is giving you a numeric value. The scale of the y always matches the same units that you're outputting. The x-axis is a little more nebulous, and I've seen, when I was first learning to read this particular chart, that was an area of confusion for me. Why is it always 0 to 100? What does that really mean? The x-axis in this chart does not mean all that much. We have to have an x-axis, otherwise we're not showing any change relative to anything else. It just means it's really just a way of breaking it into centiles, so 100. So 20, everything within that range is the lower 20% based on your output. So what this is showing you is if you care about how close these lines are together. So what this chart very clearly shows you is in the lower 20 percentile, and what I mean by lower 20 percentile is the least efficient cars, the least miles per gallon cars, the cars that are getting below, and it's just coincidence that this 20 lines up with that 20 pretty closely. But the ones that are getting 20 miles per gallon or lower, it's pretty accurate on. The cars that are getting the higher ones, it's less accurate on because the lines are different. So that's really all that the 0 to 100 line is showing you. The next most important thing to realize about this chart that can be somewhat confusing for it is this line, the technical term for it is monotonic. The expected line is always going to be monotonic. That means it, and sometimes you'll hear monotonically increasing or monotonically decreasing. That just means it goes up, but it never comes back down. So it's gradually increasing. Like a periodic function, like the sine, is not monotonic at all. It's monotonic within certain ranges, but it goes up and it goes back down. It's periodic. The reason that this is monotonically increasing, is because we specifically cause it to be. To generate this chart, the very, very first thing that you do is you take all of your predicted values, your y's, you take all the predicted values, you put all the corresponding predictions with it. So you create a data frame almost of those two, and you sort it by the expected. So if you took away the prediction, so if you took away the green line, your blue line would basically just be a line chart of showing how quickly, as you order all the cars from the lowest miles per gallon to the highest miles per gallon, just how quickly do they increase. Then you put the predicted line on it so that you show the predicted output, the model's estimation of that. And you basically, so for each of these cars, for the cars that were really there, you're plotting where the prediction was. So if this were perfect, the blue line would still be just as irregular as it was. That's just due to the data. But the green line would go on, I forget which it's plotting first. It looks like it is plotting the blue line. So you would not even see the green line because the blue line would be on top of it. That would be a perfect regression that, again, me being the skeptic, would be skeptical of. Certain things you can hit with that much accuracy, but often there's noise in it. And noise is just cars or ones that are outliers that you would never be able to predict. Like in the Titanic data set where you're predicting, did people survive or did they not? That's another data set that's very common. Usually young females made it off the Titanic with pretty high degree of probability, but there's a few that did not. And why did they not? You don't know. Maybe they tripped and broke an ankle. They just didn't make it. You can't predict those because there's no mathematical reason for it, and they're referred to as noise. So just to show you how this one, and apologize for the rapid scrolling, give anybody motion sickness. But if you look at the plot for the regression one, this is a relatively simple one to generate. You pass in the prediction, the prediction and the y, and what I do is I create. This is a very useful pandas command to do. I create a data frame. So I create a data frame completely from scratch. I think I answered at least one or two questions about data frames from scratch to people asking about some of the homework or the first program. But I create a data frame with the predictions, and I take the predicted value, I flatten it to just a list. It just makes you do that. So I have a predictant column, and then I have a y column that is basically my y test. So I create a brand new data frame of these two different lists that were passed to me. Then I sort them, and I sort them in place for performance reasons, and I sort by y. And that's what I told you. That's how you produce this chart. You sort all the MPGs. So the low MPGs are near the beginning, high MPGs are at the end. You could do it the other way. You would just have a flipped around lift chart, which would still be just as accurate. It's just the convention to put the low ones at the left. And then I plot the two lines. I create a plot of A, and I actually do not even need to keep the A and the B here. You can keep those if you want to color them. I could actually simplify this code, and probably should, so I don't use them. I plot the two lines. That puts them right on top of each other. I give them labels so that they show up in the legend correctly, and that's basically it. So that's really how easy it is to use. This is pandas. This is all Matplotlib. So you can create plots of many kinds very, very easily. And you can write them to the screen. You can render them very high resolution as PDFs or other graphic files. A lot of the some of the images, some of the charts that I did in the book are created very much in this way, and I just render them higher resolution. Any questions about any of those three charts that I did? I'll go ahead and show you. That's the last thing I wanted to look at tonight, is the next programming assignment, because I don't think I have anything else. No, I do not. And I just have some stuff about reading the lift chart, largely what I just mentioned. So the next programming assignment and there's a link to it in Blackboard as well, but I have it out here. There it is. So it's very similar. Just like before, I give you a skeleton. Or I give you a, yeah, this is the skeleton. The imports are very useful because this is literally taken from my own solution of this. So these are the imports that I used. Not that you have to use them, you can go your own way. So long as you get output that is comparable to the output that I get, that's fundamentally all I care about. I put the path in just to make it compatible with the IBM Data Science Workbench, but you can also put your own in data. If you don't put your data inside of data, that's perfectly fine. The example function, or the helpful functions that you would need, I already put into the skeleton. So you'll need to encode text dummy, you'll need to encode text index, and the numeric z-score I also gave you the missing median and the 2xy. So I'm giving you very much an indication of which of those functions I think you should be using for that. There is a data set that I use for this one, which I created. It's a toy data set, so but it does have data that are useful for this one. You can get it basically from the website. So under the data sets, the toy 1 data set. Basically what it is it's a sample data set with 10,000 rows. I generated it with a Python script. So basically what I am doing is I have data for essentially solid objects. And I give you the metal that they're made out of. There's only a few, so gold, silver, bronze, platinum. So these are categorical. And then I give you the shape. It's either a box, a cylinder, or a sphere. And then I give you the height, length, width, and weight. The weight's what you're trying to predict. So if you just plugged in the formula for what's the volume of one of these, so you don't need machine learning to do this. But you're seeing, can machine learning learn very accurately to synthesize those shapes, those solids? And it doesn't do it quite as well as you might initially expect it to do. So this is a useful data set for feature engineering, and we will, when we get into the pre-processing section, I will show you some more. Now I don't have you do any pre-processing on this or feature engineering. All you're doing is using this data set. So this is what it looks like: silver, bronze, shape. Don't try to calculate what the weight is going to be using density of metals and that sort of thing. You can, if you want to check to see that I generated it correctly. But you want to see, can a neural network learn to, so what it's going to learn to do is use its hidden layers to literally segregate the metals, the shapes, and then use these various measurements to calculate the weight. So it's a toy data set. It's one that I used in conjunction with my dissertation because it's a generated contrived data set. And it shows that even though if you just know the secret, and this is a regression, so if you just know the secret, if you know, figure out what the density of that metal is, figure out the weight per cubic centimeter, the shape, and then know the formula to calculate what that shape is, and know how I'm assigning height, length, and width, and I explained that above, you can fit the regression perfectly. But the model doesn't know that. It needs to figure that all out on its own, and you don't need to help it. Treat this just like the MPG data set. Don't treat it any different. Okay, and then what the questions are. So question, and then I give you sample output too. So question one, you're encoding the toy data set. This is really just doing an encode. This is, all you're doing is basically creating the feature vector. This is a very easy one. You're essentially just, you're encoding the height, the length, and the width. You're encoding them into z-scores. And then all these zeros and ones there, you're encoding dummy variables on those. And you're basically just, you should get a data set that looks something like this. Question two, and I do have links to the toy data set in there. You're using that toy data set again. And now you're going to do a 25% holdout for validation, 75% for training, and you don't need to generate a CSV for this one. And you're basically just training it to see how well it predicts the weights. Question three, now that you have you're going to basically use the z-scores that you got in question one from encoding it, and you're going to encode these three values. So remember how you can pass your own mean and standard deviation into the z-score? That's where you'll do it, because you don't want to calculate the mean and standard deviations on just these because there's not enough of them. You're encoding these using the mean and standard deviation that you got before. And that's very, very real world, because what I will often do is I will train a neural network or some model on a vast amount of data that we were given. But now when it's being used in the real world for production, data comes in one at a time, and I need to encode those so that they can go into the neural network. And that's what they should look like if you're using the, basically if you match mine to 1 or 2 decimal places, that's really about all I'm checking. I realize rounding can be different sometimes. And here I basically, the last two I make you do, these will be very similar. These will be very much copy and paste, but not completely. So normally the iris data set you classify, but I make it a regression problem. You use, so you have 4 measurements for the irises. You use 3 of them and the species to predict the 4th. So I flipped it around, turned it on its head. Basically, I'm just seeing, can you take my code that is a classification normally from iris and copy and paste the appropriate piece. There's really not much of a trick to this one. This is probably a pretty easy one. This is, you're just encoding iris differently than you would normally see. And then I do something very similar for the auto MPG. You'll treat that as now a classification problem. And like I said, on both of these, make sure to shuffle the data. But you are now, you're going to predict how many cylinders the car has. And as it turns out, the neural network can do this pretty near perfectly. So this is really all I'm doing with these is I'm trying to make them very real world. I'm seeing, can you take my cookbook of algorithms and apply them slightly differently than I applied them in class? And use a different data set. So I'm giving you the toy data set. So, okay, are there any questions on that? If you have any specific questions on, this is all that I have. If you have any specific questions on homework assignment 1, which is due tonight, I will be here to answer any of those that you might have on those. And I don't know where my sign-up sheet landed, but make sure you bring that back. Whoever it ended up with, bring it back to me. Okay, that's all I have for this week. Thank you very much.